So, thank you for coming to the seminar. Please join me welcoming Dr. Zhao. Dr. Zhao is a new assistant professor joining IRT in 2025 at the School of Interactive Games and Media. He received his PhD from Worcester Polytechnic Institute in August 2025, and his research focused more on building AI models and systems for real-world, enabling the real-world application in dynamic context, with a special emphasis in enabling the seamless interaction with virtual content and physical world. So please join me in welcoming Dr. Zhao, and the stage is all yours.
All right, thank you very much. All right, so hello everyone, welcome, and I hope everybody had a great Thanksgiving, and thank you very much for coming today. I know this week is difficult. Yeah, so my name is Yiqin. I joined RIT this fall. I'm a new assistant professor from IGM. It's part of CIS. So yeah, my research primarily works on augmented reality. During my PhD, I work on a specific topic called lighting estimation, and that is something I want to share with you today. Now, before we go into the technical details, I want to talk about AR in general a little bit more, right? So we have all heard about this technology called AR, right? It started from this kind of very sci-fi looking, military looking things, and then it grew into like glasses form, and then you also see mobile applications that call themselves AR. Nowadays, you also have headsets and different kind of devices. Now, in the past decades, AR technology has grown a lot, and there were hypes around it. There were higher emotions around technology. There were lower emotions around it. But with this kind of development, there's a major reason. That is the underlying technology that is supporting AR experiences is quite difficult and it's quite complex. And a lot of times, even today, some of the fundamental components do not give AR a good experiences. And one fundamental component is the ability to estimate environment lighting. Now, to put that in the context, I would like everyone to think about games and think about visual realism in general. So tell me if you have played Pokemon Go before, or at least heard about it. Okay, cool. So think about this kind of game, right? You take out your phone, you look at your screen, you will see a virtual object that exists in the physical world. Now, when you play this kind of game, you want the virtual object to somewhat look real, right? To blend into the world. Or maybe you want to do a virtual try-on kind of applications. You also want those kind of things to look real. This kind of visual realism is super important to AR because that ensures a coherent experiences. Now, that is the virtual trial application I mentioned. Think about it as trying a pair of virtual glasses or jewelries, or maybe clothes. But everything in that kind of application, you want it to look real. So today we're going to talk about how can we support that kind of realism. And the core concept in that is get the lighting correct, right? So I believe at imaging science, we know a lot about lights. We know a lot about controlling lights. So in modern computer graphics and in modern filmmaking, we know that if you want to do fancy visual effects, if you want to do realistic rendering, you need a specialized setup. You need expensive lights, you need expensive controls. But this kind of things, we cannot expect regular AR users to bring them and carry everything to a real world environment and use that for their applications. So what we really need on mobile AR, especially on phones, on glasses, on headsets, is a versatile solution that replaces all of this expensive equipment and these expensive setups with probably simple sensors and simple algorithms. So the task to achieve that is called AR lighting estimation. Now let's unpack this task a little bit. So AR applications add realism to virtual object rendering using a 360-degree representation of the environment lighting. If you are familiar with computer graphics, this kind of lighting or this kind of representation is usually an image. It's called an environment map. It could be an HDR image that represents the incident light coming at all directions at a specific position in the environment. And using an image like that, we can render a very realistic object on the screen. Now, the key challenge here is that oftentimes we have to estimate out of observation environment lighting and also in the dynamic context. Now, what does that mean? So for AR devices, let's just look at the phone, right? A phone, you have a camera on the back. You also have cameras in the front. For glasses, you can have cameras in the front, probably on the side of the glasses. But those cameras are always limited. A good example is the FOV of the camera. It's usually 90 degrees or 70 degrees. It's not going to be 360 degrees, which is something we want. And also, cameras have limited pixel dynamic range. Remember, the lighting we use to render object usually has to be HDR. So your camera and your observation of the scene is limited. And your algorithm has to figure out the scene from only limited observation of the scene. And a good way to visualize this is the part the camera captures of the scene. And this is that part compares to the full observation. Now, the second part I want to highlight is the dynamic context. So in the AR application, particularly for gaming kind of applications and entertainment applications, it's very likely the user going to use this kind of applications in the dynamic setting. That means the environment lighting going to change. The user going to carry that device and move around. And the user going to interact with the device quite a lot. So a lot of dynamic components in it, and will make the task a lot more difficult than just doing an image completion. So how do we gonna solve that? Let's start with a simple concept. Let's start with your device. Let's say it's a phone. And we're just going to look at this process of lighting estimation and how do we use lighting estimation results to render a virtual object for AR. So the pipeline is going to start with a observation, the image that your camera takes. And then you're going to choose a location in that image to put a virtual object, just like how we deal with Pokemons. And we insert the object, and we display that image to the user. Now, in this process, if the object is rendered with correct lighting, then it's going to show the good visuals. And lighting estimation happens somewhere in the middle. So a very important challenge here is that, look at the pipeline on top. In this process, we tend to choose a specific position in the environment and put a virtual object in that position. And that position is different from your observation position. Now, remember, in a light field, you have 5 parameters to determine the exact RGB or exact values of the color of the light. That means in this context, your observation is different from what you want to estimate. And you have to somehow convert your observations, transform the spatial locations of the environment, and get the environmental observation at your estimation location. And this kind of problem, we call it observation estimation spatial variance. Now, how are we going to solve that? We're going to go back to our device. So nowadays, it's not uncommon to have advanced sensors on phones. And in one of our early research work, we looked into this kind of direction of using 3D vision and 3D sensors that are widely available on AR devices to support a good estimation, good lighting estimation in spatial variance conditions. So particularly here, we use LiDAR sensors from a phone and acquire RGB and depth images of a scene. And we built a 3D vision-based pipeline that starts with basic point cloud transformations, and we added a learning-based components to do a regression task to start from here basically and estimate the omnidirectional environmental lighting based on point cloud distribution. Now, this was a paper published in 2020. That was a very different time. We didn't have ChatGPT at that time. And machine learning was in very different landscape. So some of the technology here might be obsolete, but the task formulation is still good. So in this formulation, we did a 3D transformation on the input point cloud and used that to regress the omnidirectional lighting, which is represented in spherical harmonics. And what we found is that with the correct transformation and the correct formulation on the 3D transformations, we are able to use a very small network to just fit in this kind of regression and get a really good estimation on the coefficients. Now, this compares to some of our baseline works, which was published at the same time but uses much larger network. We get even better results with with much smaller network size. Now, here are some results. So this is from ARKit, which is the commercial solution Apple provides in their AR devices. Now, this is our result, the same object rendered with different lightings. Now, you can clearly see that our result is better. This gives some more coherent lighting to the environment condition. Now, let's move forward and think about this. So now we have a solution that gives lighting estimation, and it works with AR images as the input. So can we just put this network, or can we just put this, whatever model it is, just to a AR system or AR application and just hope it to work? And can we just think about this kind of setup and just hope it to work in every different kind of real world environments? Now, very likely it's gonna fail, and the reason could be different. Now, to better understand that situation here, let's look at the inside of an AR application. So this is a visualization of AR system. There's some tasks happening, there's some data being collected. But the idea is that an AR application, AR system, runs in real time, and it collects multiple kind of data, and it is consistently doing data processing. So a lighting estimation task has to somehow integrate with an AR system in order to truly give the AR application a good user experiences at the end. And particularly, here's a good example for SLAM, which is a task that aims to estimate the device position from the camera observations. Now, it takes inputs from MU sensors, takes input from camera images, and it takes a big chunk of CPU time. How do we integrate the machine learning method we developed in previous work into this kind of system? It's the key. And this brings us to the second question, which is dynamic system resource allocation. Now, all right, sorry about that. Now let's think about this question and think about what is the center part of it, right? So let's say we just put a lighting estimation model in the phone, and we want it to work, want it to run in real time. So this kind of machine learning method usually takes a longer time to compute than the frame could be rendered. So that means you will have to skip some frames, or will have to skip some inputs. And also, your environmental lighting condition doesn't change all the time. For example, here, the lights are static. They don't change unless we control that. So for your phone or for your AR application, it doesn't have to do lighting estimation all the time. And that brings us to the core question, right? How do we know the lighting estimation quality without actually doing lighting estimation, or without actually having a ground truth that gives us feedback? So this sort of becomes an open loop kind of question. So now in the following work, we developed a mobile system that works with our previous machine learning method and provides lighting estimation in real time for Unity applications that could be run on mobile devices. So the core of our system is a triggering mechanism we call adaptive estimation trigger. This kind of mechanism starts with the same as per frame observation of the scene of the point cloud. Then we use a very smart, I personally think it's very smart, point cloud sampling algorithm to look at basically the input of lighting estimation and try to decide whether this input would trigger a meaningful estimation at the end. Now, how do we do that? We took the input point cloud and we do a spherical sample. Basically, we want to sample the point cloud not based on grid, not based on numbers, but based on their distribution of directions. So let's zoom in a little bit and look at this sampling algorithm. Now, the idea here is that on the unit sphere, or let's just say at a specific position in the scene, if you have a point cloud of the scene that is really uniform distributed at all directions, basically it's like a 360-degree image that covers all directions, then you're going to have a more accurate lighting estimation result at the end. Because what do we do for lighting estimation? It's just that we are trying to extend our view, extend our camera observations. And we found empirical evidence. We tested a few lighting estimation algorithms, and we connected the observation completeness with the estimation accuracy. And it matches our assumption here. So using this assumption, we built this triggering mechanism. Now, the key question here is that, okay, now we understand we need to test the completeness of the point cloud distribution on the sphere. And we want to test its distributions of directions. Now, how do you test that? How do you know if two-point cloud are really uniformly distributed, two-point cloud, maybe with same number of points, if one of them is more uniformly distributed than another? Now, you can test the percentage of, for example, if you can slice the sphere, you can test the percentage of areas it covers. You can also test the number of points being recorded on a specific region. But if you use percentage at the end, you're going to get a result that do not really tells you the completeness, but rather tells you just the distribution over a fixed selection of areas. Now, I know it's a little difficult to visualize that process, but let's just look at how we did this in our design. So we didn't go into the percentage direction. Instead, we used the entropy-based method. Basically, we consider the point as this kind of little dots that gives entropy values on the unit sphere. And we calculate the completeness as a joint entropy value. It is created from different levels of sphere subdivision. Basically, on each subdivision level, we slice this sphere into multiple regions and calculate the distribution of points on each region. And then we calculate the information entropy value on each region and combine them together. This gives us the end, the joint entropy on the sphere. This also applies if on a 2D surface, if you are putting points on the 2D surface. But for our case, because we are testing directions, this really the geometry meaning here is really about spherical surfaces. So using this triggering mechanism, we have successfully integrated the machine learning model we developed and put that in the real-time context. There's some rendering results. And I want to kind of continue our exploration. Now, look at this rendering results and look at a real object. Now, these are two things. Previous slides, virtual object. This slide, real object. What differences have you noticed? What is the main visual part that's different from these two slides? Right? Just look at it one more time. And I will just say it. The main difference here is reflection. So this is a physical mirror sphere. It's a mirror ball, metallic ball. It reflects the environment. But our previous rendering does not give us the ability to do reflection rendering because we are only estimating we call low density environment lighting. It doesn't represent the full geometry detail of the scene. And this is our next goal. We want to improve our lighting estimation and support reflection rendering. So reflections. And how do we do that? Our question we're looking into in this work is to leverage mobile sensors and device mobilities to understand high frequency details in the environment lighting. Now, high frequency details really means this small details like text, like small blocks on the reflections. It's in a signal processing perspective. All right, so how do we do that? Let's go back to our AR device again and look at the device. So when we use an AR device, it is a thing that we either put in our hand or put on our before our eyes, and we're gonna move consistently throughout the application. And you're gonna have a moving device and gonna look at the environment from different angles. Now, this kind of mobility of the device and naturally the mobility of the sensor creates a more comprehensive view than one single observation can provide to a lighting estimation algorithm. So around that, we built this pipeline that naturally uses multi-view observation of the scene to create environment lighting at the end. Now, we have three main steps here. One is to capture environment lighting from a moving device. We collect RGBD images and the tracking data from AR frameworks. And then we have another point cloud generation component. But in this one, we did not just use point cloud to construct low frequency details. We used point cloud also to create high frequency details. And at the end, we convert the point cloud to environment maps and use that for rendering. So speaking of mobility, and that's the most important part in this research. Mobility brings in opportunities, but it also makes things a lot more difficult because we're gonna need to handle this dynamics of moving devices. And we developed this policy around a moving device, and we basically break the observations into two parts, and we call them we call this component two-field lighting reconstruction. And the two parts we use for observations are far-field observation and near-field observation. Now, near-field and far-field really means the distance of environment to your estimation position, to where you want to put your Pokemon object. Now, for near-field, that is the environment near your Pokemon, we try to collect a dense point cloud and use that to create high-frequency details on the environment map to support the reflective object rendering. The reason we do this is that we did a measurement study and we found that for near fields, it provides a lot of important details to support reflections. The kind of percentage we get at the end is far more greater than far fields. And also for near field, because usually when you play a game like Pokemon, you naturally have this interesting point around where you're gonna place that virtual object. You're gonna move around, gonna consistently look at that virtual object. And that creates a more reliable environmental observation than, I don't know, 10 meters away from your current position. And for far field observations, that's where, maybe the background of the scene, maybe, maybe your back door, maybe just somewhere very far away from your Pokemon. A lot of time on AR devices in real world settings, our sensors are limited. And for far field observations, they're gonna either have noise or they're gonna have no data at all. So instead of applying the same policy, we developed this far field policy that focuses on recovering the environment, ambient colors and ambient tone image styles rather than creating the details. So by combining far field and near field observations, we can create the environment map that supports a really good rendering of the object and also with reflections. Now, here are more visualizations. So for this one is our result, and that is also from ARKit, Apple's commercial solution. You can clearly see that compared to this physical mirror ball, this real object, on the near field side, on this reflection side, our rendering result provides more detail, and these are all correct details. You can see this text being rendered, this little red block being rendered. All of those details are missing from Apple's AR rendering result. But here's some more comparisons. So compare from our results to the real object. I would say on the reflection side, it's pretty close, but there's one major part missing. That is the top part of the sphere. We're missing reflections on this side because these are the part corresponds to far field rendering, and our devices could not have reliable data sources on those areas. But we're gonna move forward. We're gonna continue our explorations and see if we can have methods to solve that. And that brings us our latest work on lighting estimation, where we use generative models to compensate for device sensor limitations and device mobility limitations. Now, a little bit background on generative AI, particularly for image generation models. So we have this kind of task that being quite widely used for generative models called outpainting. So the idea is that you give generative model one image as input. The model will follow the context of the image and extend that image. And that model can do this again and again. And we'll create the larger image at the end, but follows the exact context and visual details on the original image. Now, that kind of gave us hope for lighting estimation, right? Because the one major problem about lighting estimation is that we have only limited sensors on devices. It doesn't matter what device we use. It could be, mostly it's about limitation in FOV. So why don't we just use generative models and apply that to create an environment map? And not only we can create more detailed environment map, but also we can create environment map with basically anything. We can control the process and we can create the environment details as we want. So it's really tempting here to ask. This was work we did in 2024, and it was really tempting for us to ask, is lighting estimation, is the task itself just one more generative model away? Because a lot of computer science research at that time were like this. A generative model solves a previously impossible task. But I would say now the answer is no, because we're gonna look at some of the complexities inside the task. So let's say we're gonna put a generative model in this lighting estimation problem, and we're gonna start with your AR device observation of the scene, maybe some other conditions, some text prompts, some other things that the model needs, And we want the model to generate a full image. Now, if you look at this process, starting from the image on the left to the image on the right, the field of view of these two images are vastly different. And on the right, you have a lot more information on the image than left. And that means this is a sharp information increase process, and that is very ambiguous by itself. So the generative model has to figure out a lot of this creative process and put in the right details and put in the right context on the image to make sure that the output is reasonable. But you don't know the ground truth. You don't have a constraint on that. And a lot of times in a real world setting, things could be complicated, the model could fail. So how do we address this ambiguity in the process is one of the key. And also in the real world lighting, in a real world environment, lighting conditions are complicated. For example, with different time of the day, you're gonna have different sunlight colors. And in indoor environments, where we use artificial lightings, you're gonna have also different light colors. And that means different temperatures of the light. This creates a very different distribution than typically what we use to train lighting estimation models or image generation models. So a model that is targeted for lighting estimation on mobile AR has to deal with all these dynamics and all these complexities of environment lighting in real time. So let's look at our solutions. We start with an AR device. And this device will look at the environment, look at the surrounding world. And then by sensing the environment, we can collect a lot of information. For example, RGB image, that was the low FOV image we showed before. And also, you also have ambient light sensors on the device. And if this is a public space, or if this is a space that is known to the device, you can also have the semantic map of the environment. So our design here is that we want to use more information of the scene and use a rich context to ground the generative model in order to generate a more accurate result at the end. And also we have a novel formulation to break down the task into two parts, so that not only we can complete the camera image into an environment map, but also estimate an HDR environment map from only LDR, standard dynamic range camera images. Right, so like I mentioned before, one of the key is to handle the ambiguity. Now, this is a great example. We start with a low field of view of observation, and the model and our pipeline handles the rest and make it a full image. So how do we handle the ambiguity? So one design we use is to use more context, because a lot of times information are hidden in different sensitive. We don't have to just use RGB images. We can use a generative model conditioned by all this data, and it is extendable to our system. We just need to retrain the model. We use all this context to control the model and make it generate a more more comprehensive view of the environment. Now, second design is that, the second design is that we do not ask the model to only generate one image. We ask the model to generate a bunch of outputs, and we use an online algorithm to decide which one is the best. And that algorithm runs very fast so that we can choose the right image and also adjust its color in real time and use the right image to render virtual objects. Now, here are more results comparing Clear, which is our latest work, to LiDAR, which was the previous work. So you can clearly tell that the reflection part are still there. Right? You can still see near field reflection. Well, for the far field, we added more details. For LiDAR, it's blurry, it's not very informative. But for Clear, you have a lot of details, and this looks like that. So I want to do a quick summary. These are some of the work I did before for solving lighting estimation on mobile AR. I started from here that we developed a small neural network just for estimating low frequency lighting. Then we moved to developing a mobile system that can handle resource allocation and dynamic point cloud sampling in real time. And then we moved to supporting reflections and also use training models to compensate for sensor limitations. These are some of my major works done during my PhD. All right, so since we still have a little bit of time, I want to talk more about more research related to lighting estimation as well as some of the things in general to AR. Right? So lighting estimation is really a good representative task to AR because it represents, it kind of shows that AR devices are very complicated and AR systems are very complicated. And the kind of challenge we need to face in the real world setting is very difficult. So we basically put in a lot of different methods we can use to solve this task. We have a mathematical model, we have a neural network model, we have good programming, we also have generative models just for solving this task. I would say personally, I do enjoy the process, and I do say AR will gain a major development in the future as we have more models and learning algorithms that can compensate for sensor limitations and address a lot of the real world dynamics. Speaking of that, I do want to bring in a side topic. This is also a work we did before, just looking into the privacy issues related to photorealistic rendering in AR. So let's say now we have this very fancy, very accurate lighting estimation model, and we want to use that in a real-time application. We want to do a live streaming to the user, maybe put that on Discord. And we want to put some virtual object on ourselves. In order to have those virtual objects to be rendered realistically, we need a good environment lighting. We need all the details of the environment. Just like physical objects, just like physical reflective objects. Those virtual objects can also reflect information in the scene. And a lot of times, users do not, or simply are not aware of this. And when they turn on their application, streaming applications, they're gonna be surprised. Some of the things gonna be reflected on virtual objects as well. And that could bring us a user privacy concern. And this work, basically, we looked into how to solve this kind of privacy issues without sacrificing on rendering quality. And also without introducing significant delays of the system. But in general, I would say as we have better and better AR technologies, and we are bringing virtual and real worlds together, user privacy is going to be a more important issue in the future. And I do hope more people could look into this. And that's it. And that's all for my talk today. Thank you very much. Happy to take any questions.
When you're, I think it was the spherical angle entropy calculation. Can you give a little more insight into what coordinate system you used for that type of calculation? I assume it's a constant solid angle, or
oh, it started as a Cartesian coordinate, just XYZ, and then we projected all the points to this spherical surface, and we ran the calculation on the surface. So coordinate system wise, I don't think it's we didn't use anything fancy.
Yeah. Okay. So your sphere subdivision levels have varying solid angles then.
Yeah.
So two kind of related questions. First, if you have any idea, your ground truth here doesn't really have much to do with human perception. And
Mhm.
the end result of this is to try and create images that humans believe.
Mhm.
And it's kind of unclear what amount of like physical realism or physical accuracy you need to achieve that.
Mhm.
Have there been any studies that are relevant to kind of measuring the threshold for human for what's believable and what's going to raise concern among your observers?
Okay, very good question. So, true that for now, this task or in general, lighting estimation models is far away being perfect. Right? A lot of times it outputs somewhat creative work rather than the physically accurate results. There were studies just focus on measuring the visual qualities between foreground and backgrounds without using a ground truth. And there are also metrics that tend to align more with human perception than the physical accuracy. For us, we did a user study on our last work. Was a fairly simple one, but what we found is that our models gave the best estimation result compared to some of our baselines, which also use generative models. But as a direct answer to your question, I would say this is still pretty much ongoing research, and there should be a lot of work to be done just to look into the realism and quality of generative models, not just specific to lighting estimation, but in general.
Okay, then another quick question is kind of related. That when you put your lighting on this object,
Mhm.
based on what you're putting on here, you're implying something about the illuminance, about where it is in the world, or the illuminants, where they are in the world, and their color characteristics, and and if that were inconsistent with, say, the shadows cast by this object you're putting things on, that you're drawing on, to say that might trigger the observer to say that looks really unrealistic.
Mhm.
And so it seems to me like those two problems might have to be solved at the same time. The
Right.
shadows cast by the object has to be consistent with the lighting on the object itself. And so I wonder, do you have any opinions on that? Am I guessing incorrectly, or?
No, it's very good. That's true. So one motivation we did HDR estimation in this work is that we want to support shadow casting. Because in order to cast shadow, you need to have different intensities at different locations, different directions. So you know this side is brighter than the other side, and shadow goes this way. But for our evaluation, in all of our work, we just focus on lighting estimation, just on the random result. But I would say, after we put this in a real application, after we've seen the result, shadow is really an important part. Without shadow, it's really easy to tell that this is like a floating object. It doesn't look real. And it's an important task need to be addressed alongside with lighting estimation. We sort of did that in the last work, but we didn't really look into the measurement of the quality on that.
Thanks.
I'll just follow on from Gabe. So, really interesting work.
Thank you.
Nice. But there's a body of work on the perception of illumination and, related computer graphics and realistic rendering. And turns out people are not so good at estimating, luminance, and also not good at recognizing correspondences between reflections and environments.
Mhm.
And if you don't know about that stuff, it could be very useful to you, because it could, make it easier for you to do what you want. So.
Yeah, I agree. Yeah.
So this is kind of like comment or slash question that's kind of building off of Jim and Gabe brought up, but like, I was just like looking at the example you gave of like that reflective sphere and your generative AI method. And well, I guess first of all, like one comment I have is like I feel like the lit AR like rendering, like kind of building off Jim's point, I feel like that actually looks pretty good to me. Like if I was like not looking directly at the object, I was like, say if I was in a VR environment, I was like making a sandwich in the VR environment, I might not actually like, I wasn't looking if I was actually interacting with that sphere, I would actually be like not notice anything wrong with it. And kind of the converse of that is like generative AI sphere had like some the final method used that had these very like detailed streaks that seemed to be capturing like the ceiling, reflected on the ceiling. And it actually struck me that felt like it looked a little bit, yeah, like those little like brown stripes, high detail stripes. Like it kind of just kind of subjectively, it feels like that it's like too much detail, in the sphere. So yeah, so I was kind of wondering like how you'd approach figuring out what are you trying to capture, like what's the most important thing to capture, that
Right.
might have something to do with the how people perceive these objects. But yeah, I guess the question that's I'm kind of building off that comment is like what's like your what are you aiming for, like is there like a metric or like
Right.
stuff like stop like when we'd be like, okay, this is good enough, like we're
Right.
definitely-
Good question. So for our evaluations and experiments, we do have ground truths for all of these things that are images captured right at this position with 360 cameras. We use that physical accuracy to do the evaluation. But personally, I agree that linear, the result is pretty good. Certainly, at a certain point, while I was using that system, I feel like I got tricked. I feel like there's a real thing in front of me, but it's not. But I would say these are very tricky objects. Typically in an AR game or AR application, you don't see these kind of things. You see more like a gamey kind of objects with a little bit of reflection, or some part of it are reflective that needs to capture the environment lighting. But you don't see like this fully reflective, perfectly circle kind of object. The object like this itself is all natural. So I would say definitely on the evaluation side, there are a lot of things to do just to align physical accuracy with human perception, especially for tasks like this that we cannot achieve perfect physical accuracy. Maybe achieving a better human perception result is more important. Thank you.
These reflections, are they only working for like a standpoint image, or if you were like to move around the ball, would your reflection change with your player?
Yes, if you move around the ball, it changes in real time.
Yeah, I mean like in the actual like virtual reality, but it changes as well.
Yeah, it changes in real time. Yeah.
For light estimation, especially in relation to moving, I sort of got the impression that movement is a double-edged sword, because you both have to account for it, but it can also give you more accurate information about what the sources of light are. My question is, has anyone ever investigated a Bayesian approach for sort of updating what the model sees as the ground truth regarding the sources of light, their luminosity and frequency?
Personally, I don't know any. We try to do something similar to that. We did a measurement on the mobility pattern versus the actual observation at the end. But we didn't go as deep as what you just described.
Yeah, because like if you start out with an image, you presumably have some kind of guess for what's generating the light. But if you turn a little bit, then that likelihood changes, and by Bayes' theorem, yeah, it's a whole thing.
Yeah, agree. Yeah.
I'm curious about the edge processing that goes on and what that contributes. So I think it was like collaborative estimation. It said, like, if I turn off the lights, will this ball no longer reflect anything based on the edge processing?
Which work do you mean? The last one or the AR?
I believe it was in the AR.
Okay.
There was an edge processing component.
Oh, I see. Okay, so in this work, everything runs in real time. So if you turn off the light, the lights on the ball will just disappear. So it will just follow what the camera is observing in the scene.
Sorry, I meant here. That was my bad. It's like after the map is generated, there's edge model.
I think. Do you mean this? This part? The edge server?
No, it'd be further, never mind,
Uh,
further forward.
okay. Okay, I think this, right? This,
Yes,
Yeah.
that's what I'm curious. about.
Okay,
Sorry,
okay.
yeah.
right. So this part also runs in real time. This part runs it on the device, and the inference of those models runs on the edge. So that's why this is called a collaborative estimation. And to answer your question, if we turn off the light and here, the on-device pipeline will immediately react and change the colors of the estimated immersive lab.
Thank you.
Yeah.